What is that sound? Well, that sound can only mean one thing. It's time in physics to unlock the amazing world of waves. All right, so let's start talking about waves. There's so much to learn. First thing I want to point out, if you stuck with me and studied electricity and you went all the way through it, do you know what goes on inside wires? Well, yeah, okay, at least a little bit. You know how that works. You know how resistance works and voltage, electrical pressure and current. You know that stuff. But do you see reality different? When you clap your hands, do your hands ever touch? Well, no, they never touch. Electrical repulsion is what stops them. Is there really anything here to speak of? No. Matter, there's so little of matter here that my hands should be able to go right through each other. But they don't, because of electrical forces. When you look around your world, everything is due pretty much to electrical forces all over the place. When you see a color, first order, third grade understanding is, okay, it's green because it's absorbing all the other colors, reflecting green. Great. Physics allows you to ask the question, how come it's green? How come it reflects green and absorbs the other colors? Now, we don't get to teach that in high school physics, but it has to do with the bandwidth of the electrons. So electrons control the world around you. When you study electricity, you get a completely different view of the world around you. Same with waves. You might think we're going to study waves you see on the ocean, or maybe a little bit about sound waves or light waves, and yes, we are. But at the end of all of this, you will see the world differently. It's very fundamental makeup. You will see differently because you've studied waves. So let's get going, shall we? First of all, a couple things about waves. Number one, waves transfer energy without transferring mass. So if you're sitting back there in the back of the room and I'm talking, what you're hearing is energy I'm creating at my mouth, my vocal cords and pushing air out, but you're not getting the air I'm exhaling. All right? That's not getting to you. The waves are getting to you. Okay? So it transfers energy without transferring mass. You can also consider it to be a ripple carrying energy away from a disturbance. Either of those things are reasonable ways to start thinking about waves. So let's start there and continue, shall we? All right, so first of all, we could talk about there's two basic kinds of waves. One, there are mechanical waves. Mechanical waves require a medium to move through. Okay? Require a medium. So what would be examples of a mechanical wave? How about a sound wave? There was a movie out years ago, and the byline, you can tell how this movie was. In space, no one can hear you scream. Yeah, that was a perky movie. But if a rocket is going off right next to you in space, can you hear it? No, there's no air to carry it. That sounds so weird to us, but without air, nothing sounds at all. So it requires a medium. So a great example is sound waves. But how about seismic waves? They're popping all over the earth. Earthquakes all the time are transferring their energy through waves. Water waves. And turns out in any other material, basically you have wave propagation. That's a lot like sound waves, though. If you listen through big plated steel to somebody banging further down, if you're listening on the side of a ship and somebody's banging on the side of a ship a long way away, you can hear it right through the metal. So that would be an example, essentially, of a sound wave going through metal. So that would be a good example of all of that. All right, so that's mechanical waves. The other is electromagnetic. Well, electromagnetic waves are disturbances in the electric field. Now, that can happen simply because a charged particle is accelerating. That will create an electromagnetic wave. right? The best example we have is light, right? But when we say light in physics, we don't just mean the light your eyes can pick up. If you look at your reference tables on page 2, you will see that there is this great and powerful electromagnetic spectrum. These are all the versions of light energy, starting on the left side with really short wavelengths. Really short wavelength energy. Gamma rays. It's the most powerful waves we can possibly get. Gamma rays. Gamma rays are really potent waves. If you set off a nuclear device, a lot of destruction right next to the explosion is because so many gamma rays are coming out, they cause things to just sort of fluoresce and disappear or something like that. So gamma rays, they're terrifying. X-rays. How come the technician always leaves the room when they X-ray you? Apparently they're safe for you, but not safe for them. Oh, they're not safe for you either. There you go. Don't worry about that. Well, that's true. We make it safe because you don't get a lot of X-rays and they don't leave the X-ray machine on and go out to lunch. That would be bad. But if they stayed in the room with you, that means every time they give X-rays, they're getting X-rayed themselves. That would also be bad. So you getting a little dose of X-rays, not a problem, but a huge dose, okay, that's a problem. So we try to minimize your dose of X-rays. The next one is the wavelengths are super short, but getting a little bit longer, so they're not quite as energetic. The next one is ultraviolet. Now, you know you're not supposed to get huge exposure to ultraviolet light. It causes skin cancer. That ultraviolet light has enough energy to get into your skin, not through you like an X-ray, but still can get into your skin and thus into a DNA molecule. And if it cleaves that DNA molecule and cuts it in just the right place, that DNA molecule doesn't know essentially to turn itself off or to kill itself. And it might press the copy button and start reproducing itself. And yes, then you have skin cancer. And if your body doesn't identify it and kill it, you have serious skin cancer. So ultraviolet light is dangerous in its exposure like that. Basically, if the sun is between this V shape, you don't really want any part of it, or you certainly want a big hat on and ultraviolet light blocking clothes. When the sun is outside of that range, generally before 10 o'clock, after 2 o'clock, it's much safer for you, but it's still, you don't want heavy-duty ultraviolet light exposure. You also want to pay attention to any things on your skin that seem like they're growing or unusual. That might be that skin cancer stuff. Ultraviolet light, dangerous for us. After that is infrared light. Oh, but wait, right in the middle, right next to ultraviolet light, right before infrared light, there's this tiny little band, and I mean a tiny little band we call visible light. Now this happens to be what your eyes can actually see. You can't see infrared, you can't see ultraviolet, nor can you see any of the other waves. But you can see a tiny band of electromagnetic radiation. It is where the sun puts out the bulk of its radiation, so it would be the best band for you to pick up optically. So our eyes can see that. That's visible light. And we have colors. We have colors, right? The shortest wavelength of visible light is your violet. Then we go blue, green, yellow, orange, red, as we go up the visible light spectrum. Where do these colors come from? We don't want to get into it. It's kind of psychology. Your brain needs to have a code in it that will identify a particular wavelength of the light you see. That's what color vision is. So color is really inside your brain, and it's a way of identifying these wavelengths. But beyond visible light, then we have infrared. We have, after infrared, when you get longer than that, you have microwave radiation. And we even have then radio waves that get very, very long. They can be many kilometers long, these radio waves. Well, if very hot, vibrating fast objects are producing the short waves, what's producing the long waves? Something very, very cold, moving very slowly. So that's the great electromagnetic spectrum. Light, then, is much more than we would think. Let's continue on with our talk about waves. we need to draw a wave and identify its parts. Now, a wave is rightly considered to be a wiggle in time. Here's an object wiggling, and here are the waves radiating away from it. All right? So, a wiggle in time, vibrating object, and then how fast do the waves move away. We'll talk about what governs the speed of waves, but let's make an idealized wave. Let's see if I can do that, an idealized wave. There you go. That is one complete wave, all right? Let's talk about some parts on this wave, all right? First of all, from the base level, either all the way to the top or base level all the way to the bottom. Now, if I've drawn it right, that should be the same distance, but that is known as the amplitude. It's the amplitude, dude. So, amplitude, how big a disturbance is. Now, if you think about an amplifier, what is an amplifier doing? It's making bigger sound waves, so it's making the amplitude greater. Makes sense? This distance, well, I think I ought to draw another wave here because that'll make it a little bit clearer. All right? So I need to draw a series of waves here. The distance from here to here, from one crest to another crest, is a wavelength. And this is the Greek letter lambda. Lambda will always stand for a wavelength from now on for the rest of physics. In other physics, as you get into college, some of the other variables may change. They do that a lot. Roll with it. Lambda, as far as I've ever seen, will always represent a wavelength. Okay, so lambda is a wavelength. Crest, trough. There's a trough, an upside down crest, as it were. Well, the next thing we need to talk about is frequency. Now, it's hard to do that with a static drawing, but how about, you'll have to use your imagination with me a little bit, but how about we're talking a wave train like that. And from this time, that wave is moving out. 1, 2, 3, 4, 5. It moves, 6. So it moves there. It moves 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths, 6 wavelengths. 6 waves. If those 6 waves, if I'm on a dock and those 6 waves pass me in 1 second, that would be the frequency. How many disturbances per second? So how many complete wavelengths pass you in 1 second? That's the wave's frequency. Now the units of frequency are going to be 6 cycles per second. That is 6 hertz. And a hertz is a 1 over second. Okay? So 1 over second. That's odd, but that's a hertz. The unit is 1 over second, or reciprocal second. All right? Now we can start talking. Imagine, if you will, work with me on this. You're sitting in your car. There's your car. There's the back of your car. And there is a railroad crossing, ding, 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 coming down. And here comes a freight train. And I draw a little smaller so I can fit the whole thing. All right, freight train, and there's 1 car, there's another car, there's another car. So we have 3 cars passing you in 1 second, and each car is 20 meters long. From the center point to the center point, 20 meters. And if 3 of those cars are passing you in 1 second, each car 20 meters long, 3 of them pass in 1 second, how fast is that train going? Can you figure that out? Well, I think you probably came up with it's going 60 meters per second. Let's look at the formula we figured out to do that, okay? This might be useful. The formula, then, we have just put up in our heads is the velocity of the train equals the frequency, how many cars have passed you per second, times the size of each car, or if we're talking waves, the wavelength. So V equals F lambda is our very first formula. That will allow us to calculate how fast a wave is going. So remember what the units are. Frequency is 1 over S. Well, wavelength, that's a length. That's a length. What do we measure length in? Excellent. Meters. So what's 1 over seconds times meters? That's a meter per second. And a meter per second, sure enough, that's velocity. So this allows us to calculate velocity. Why don't we try a velocity problem? I'm glad you suggested that. Let's do a velocity problem. So, I don't know, what would a good velocity problem be? I've got one here somewhere. Okay. Well, I have a problem for waves moving down a string. Who knew they had a velocity? But you know what? If you stretch out a piece of string and you tap it on one side, you will see that disturbance run down the string. If you have it tight, it'll go pretty fast. So we'll say waves moving down a string have a frequency of 30 hertz and a wavelength notice universal sign for wavelength, and a wavelength of 0.13 meters. What is waves velocity? And we have everything we need to solve that problem. So, as always, givens, write it out, capital G, underline it. You're going to college soon. Make sure you're doing this the proper way. It will, believe it or not, impress people. Okay? Givens, F equals 31 over seconds. You might as well put it in the correct units right away. Wavelength equals 0.13 meters. V equals our question mark. Formula, V equals F lambda. Again, if I had to rearrange it, that would happen here. I don't. V equals F lambda. Please make sure you rewrite that. Now equals 31 over seconds times 0.13 meters. Now it's time for your calculator. And if you do some calculation, I'll give you a second. All right, did you get 3.9 meters per second? If you did, you calculated that wave's velocity, and you did it well. Good job. All right, well, that's how we would look at that. We have really one more thing to look at with waves, and it's a really important consideration because it starts you down the road of how you work waves, of how you can make truly powerful events with waves if you start understanding this. And you can understand certain natural events. So I'm going to have an equilibrium position. Going to make a wave. All right, on this wave, I'm going to start plotting up some points. A, B, C, D, E, F, G, H, way over here, back to I. All right. So, what we're talking about now is the phase of a wave. When we talk about a single wave, if we go from here to here, that's an entire wave. We describe that in its entirety as being made up of 360 degrees. We use degrees all the time, so 360 degrees. So consider, we're at 0 degrees here. We're at 360 degrees, which would be, of course, the same as 0 degrees again. But if that's 0 and that's 360, what's that point? Good, that would be 180 degrees. If that's 0 and that's 180 degrees, what is that? Ah, that's 90 degrees. What's this one? 270 degrees. So that is how the wave is made up. Now when we talk phase relationships, we're talking, if you want to be in phase with a part of the wave, you need to be 360 degrees away from it. Then you'll be in phase with it. So the question shows up as, what is in phase with point A? Okay? Oh, no. Let's go easy. Shh. Let's go easy. What's in phase with point B? Ah, there you go. Point F is in phase with point B. I think you can see that. What's in phase with point D? Ah, you see point H is in phase with point D. Now we could do a harder one. Now what's in phase with point A? Some of you might be tempted to say C because it's in the same place. Consider it this way. Consider these waves are on the ocean and they are moving in this direction. And all these dots are boats that are just sitting on the water, and they're not moving on the water. The waves, however, are coming through, and they're rising or falling based on the waves. None of them are getting sunk, okay? So they have to ride on top of the waves. Well, what would happen in the next moment for boat A? I think you'd see there would be a downward wave here coming for it. So A would be heading down in that case. What's happening to C? Well, as this wave comes, C is going up. That's not in phase. In phase would mean they're both about to be doing the same thing. As a matter of fact, they're about to be doing the exact opposite things. That means they are exactly out of phase. That is to say, 180 degrees out of phase. Oh, good to know. So what is in phase with point A? Ah, can you see that point E would also be headed down? So point E is in phase with point A. And furthermore, if you look all the way over here, is point I also going to be going down? Yes, point I is also in phase with point A. Great. What is in phase with point C then? Can you see that? Oh, G. If the waves are moving this way, G is going to be going up. So C and G would also be in phase with each other. Good to know. Okay, so those are phase relationships. Phase relationships let you do powerful things. For example, start it with somebody swinging on a swing. So here they are on a swing and I push them. They go out and they come back. They're right here again. Is this a good time to push them? Or am I 180 degrees out of phase with them if I try to push them? Well, the fact that I'm going to be knocked over as they come back and hit me might suggest that I've done something wrong. On the other hand, I push them. They swing out, they come all the way back, and now they displace all the way to that side. They come back here. Now, if I push them again, am I in phase with them? You bet. So this push will add to the amplitude of their wave. Yes, somebody on a swing, that's a wave. That works just like a wave. Okay? So you push it, swings by, you push it again, okay, by, comes back, you push it again. If you stay in phase with it, you could get them going higher and higher with gentle pushes. In other words, your push is stored in it. And I always ask people, could you empty a bathtub with one hand relatively easily? If you had a full bathtub, could you empty it with one hand? Say, they usually are like, no, not unless you pull the drain plug. Yeah. Could you empty it in a different way? Now, granted, don't do this. This will not make you popular. But imagine if you put your hand in the water and you slosh the water to the front. The water comes surging past back to where your hand is, and then goes to the other side of the tub. Then it comes past you again. What if you are exactly in phase with it and slosh it forward again? Comes back, goes up, and you slosh it forward again. And every time the wave comes back at you, coming the right way now, so you're in phase with it, you slosh again. Will very shortly the water start flowing out of the tub? Yeah. Could you empty the tub or largely empty it with one hand? Well, yes, you could if you did it this way. So these relationships, they enable you to do very powerful things. If we get to this drink again, or this wine glass, no, my hands are all covered with chalk dust, and that really messes this up. But why does that work? Turns out my finger has to be exactly the right stickiness. So if you'll listen, you can hear that little high ooh. If my fingers are exactly the right stickiness, so they grab and stick and grab and stick and grab and stick, and as they move along the top, they reinforce the sound that is natural in this. Now this is largely full of water. Let me empty some of the water. You can hear a different sound. Yeah, you hear a different sound. This is resonant at a different frequency. So we will start talking resonance with all of this. This all becomes really quite powerful, fascinating. Welcome to the world of waves. This gets cool. There's a lot of stuff that this has to do with. Makes a lot of sense in terms of resonance. Pretty much every object has a natural resonance, meaning we can mess with stuff in big ways. So we'll be back at you, teaching you a few more things. But that's the start of waves. I hope that helped.